Hello, my name is Yunus Rizkiaawan. Today I will explain about dynamic programming in operation research. Before I explain about dynamic programming in operation research, I will introduce myself and our group. There is Maulana Fajar Mulyani, Yunus Rizkiaawan as myself, Putu Krisna, Nurhudha febri, and Nicodemus cahya. We are from Industrial Engineering, President University. We start from definition. Dynamic programming, or DP, is a technique used to solve a multi-stage decision problem where decisions have to be made at successive stages. This technique is very much useful whenever if an optimization model has a large number of decision variables. It is not having any generalized formulation. Method used to solve a DP. In this section, we are going to discuss two methods to solve a given dynamic programming problem, or DPP, namely 1. Calculus method. 2. Tabular method. Characteristic of a DPP. Merit and demerit of a DPP. Merit. A complex problem can be split into a series of interrelated sub-problems and can be solved easily. 2. It is highly flexible. 3. Built-in sensitivity analysis. 4. Computational, saving over computer enumeration procedure. Demerits. DP is conceptually powerful but high degree of expertise and insight required for the efficient formulation of the problem. 2. More storage space is required in the computer. 3. There is no unique algorithm. Review literature. Deterministic dynamic programming model of a tool replacement. A company needs to have machine for the next year. As the machine age, annual operating costs increase, so the machine must be replaced with a new one. The price of the machine in year I is I. The annual cost to operate an old machine J is J. Every time the machine is replaced, the company receives a compensational amount for the old machine as an exchange value, and T, or G, is the exchange value for machines that have a lifespan J. At the end of year N, machine can be sold for fee J, where J is the age of the machine. Given the age of the machine at the beginning of the first year is Y, it is necessary to determine an equipment replacement policy for the machine that can minimize the local costs for the following year, keeping in mind that a replacement decision can only be made at the beginning of year. It is assumed that the annual operating cost and the exchange rate depend only on the age of the machine. Furthermore, dynamic programming models and solutions will be formed. The dynamic programming model for this problem involves stage N, which corresponds to the planning period year. At the beginning of stage I, the state Si can change according to the age of the machine that has used in the previous year. There are two possible decisions to make, which are storing the current machine or replacing the machine with a new one. If the company decides to keep the machine, the only cost at this stage is the operation cost of the machine. If the decision is to replace the machine, then the annual cost will include the price of the new machine reduced by the new one machine. The cost at I is CI, which depends on the current machine age and the decision taken. The formula is like this. Optimal value function. The minimum cost to have a machine from the beginning of year I to the end of year N or beginning of the year n plus 1 with the age of the machine at the beginning of stage I has changed to Si. Optimal policy. Replace or keep. Transform function. This function shows how to state for the next stage change according to the current stage, and decision. The formula is like this. Repetition relationship, the formula is like this. Boundary conditional, the formula is like this. So we are going to problem example. A company needs to determine an optimal replacement policy for the machine. They are 2 years old for the next 4 years. The company has a requirement that a 6 years old machine must be replaced. The company has two choices, namely to replace R or keep K. The diagram is like this. The graph shows that the beginning of the second year, the probable age of the machine is 1 and 3 years. At the beginning of the third year, the probable age of the engine 1, 2, and 4 years. And for the beginning of the 4 years, the probable age of the engine is 1, 2, 3, and 5 years. The graph also assumes that the machine will be safe at the beginning of the 5 years regardless of age. The cost required to buy a new machine every year is $100,000. Given the tables as follows, where T is the life of machine in years, R is the trade in value, C or T is the operating cost, and S T is the cost of purchasing a new machine. Exchange rates and operating costs and costs for purchasing new machine in dollars. Determine the optimal solution is replacing machinery in the company. The diagram is like this. K as keep or replaced, S for sale. The answer is determining a suitable solution for the age of the machine at each stage is rather complicated. At the beginning of the first year, the company had a 2-year-old machine. The company has two choices, namely to replace or R or keep K. If a replacement occurs, then the beginning of the second year the company has a new machine that is 1 year old. If there is no replacement, then at the beginning of the second year the company has a machine that is 3 years old. This continues from the beginning of the second year to the 4th year. If a 1 year old machine is replaced at the beginning of years 2, 3, and 4, then the age of the engine is 1 year at the beginning of the following years. At the end of year 4, the company will save the engine S. The solution in the figure above is the same as determining the longest road. In this problem, we look for maximum income from the beginning of the first year to the end of the 4th year. We will use the table to solve the problem. Note that if the machine is replaced in 4th year or the end of planning, the income includes the remaining value of S1 from the replacement machining. Similarly, if in the 4th year the machine with the age of T is stored, the residual value will be T plus 1. Stage 4 shows the age of the engine in the 4th year. From figure A, it can be seen that in the 4th year, the life of the machine is 1, 2, 3, and 5. So that the value of T, 1, 2, 3, and 5 can be determined. The recursive equation in stage 4 is The formulation is like this. In the first column of table 1, so the values that have been determined. The second column is obtained by entering a known value in the method of table A, and entry in column F4 is obtained by finding the maximum value between the second column and the third column. Decision can be made based on a column containing the maximum value specified in the fourth column. And stage 3. As in stage 4, stage 3 shows the age of the engine in the third year. From figure 1, it can be seen that the age of the machine in the third year is 1, 2, and 4, so that the value of t, 1, 2, 4, can be determined. Because at the stage 4, we have the value f4, t, the recursive equation at stage 3 uses the second equation. The formula is like this, and we look table 2. In the first column, table 2 shows the values that have been determined. The second column is obtained by entering a known value in the method of table A, and entry in column F3 is obtained by finding the maximum value between the second column and the third column. Decision can be made based on a column containing the maximum value specified in the fourth column. Stage 3. As in the previous two stages, stage 2 shows the age of the machine in the 2. From the problem of a figure A can be seen that the age of the machine in the second year is 1 and 3, so the value of t, 1.3, can be determined because in stage 3 we have a value of F3. Then the recursive equation in stage 2 uses the equation the second is. The formulation is like this, and you can take a look at table. In the first column, table 3, shows the value that have been determined. The second column is obtained by entering a known value in the method of table A, and entry in column F3 is obtained by finding the maximum value between the second column and the third column. Decision can be made based on a column containing the maximum value specified in the fourth column. Stage 1. As in the previous stage, stage 1 shows the age of the machine in the first years. From the method of figure A, it can be seen that the age from the machine in year 1 is 2, so the value is of t, 2, because in stage 2 we have value of f2, t, when the recursive equation in stage 2 uses the second equation. The formulation is like this. In the first column, table 4, shows the values that have been determined. The second column is obtained by entering a known value in the method of table A, and entry in column F2 is obtained by finding the maximum value between the second column and the third column. Decision can be made based on a column containing by maximum values specified in the fourth column. So we are going to stage 1, or the last stage. Figure A summarizes the optimal solution. At the beginning of the first year, given t, 2, the optimal decision is maintain the machine. Thus, at the beginning of the second year, the machine will be 3 years old, and the optimal decision is to replace the engine. At the beginning of the third year, the engine will be 1 year old because it has just been replaced. So the optimal decision is to maintain the engine, and in the fourth year of engine life is 3 years. The optimal solution is to maintain the engine. Optimal alternative policies starting from the first year or key are K total cost required is 70 to $800. Thank you. I get the reference from Script Universitas Sanata Dharma Yogyakarta, and I also thank you to my lecturer, Dr. Edwin Setiawan Nugraha, Magister Science, President University, and this is all for me. Thank you.